All right, so this morning we started looking at work specifically, okay? And then this afternoon, we're just going to take it one step further and we're going to introduce this idea of kinetic energy, okay? So the energy, basically kinetic means like moving. So it's the energy that a moving object's going to have, okay? And how work plays into that. So according to the definition of work, the total work done on an object by the net force is, we can denote it work total, and this is just a recap of this morning stuff. We could add up the forces, cosine theta delta D. Okay, and work done causes the speed of an object to increase, okay? So when we do work on an object, we're obviously applying a force for some amount of distance or displacement. The speed of the object is going to increase in those instances, right? And so this causes the energy of the kinetic energy or the object to also increase, okay? The object gains kinetic. Okay? So there's two things that kinetic energy depends on, right? One is the mass of the object, and the second is how fast it's moving, so its velocity, right? Okay? Since work is energy transferred to an object, if the work results in an increase in speed, the kinetic energy also increases. Okay, so if the work done on the body causes some form of acceleration, I suppose, right, then the speed will increase, right, and the kinetic energy will go up because it's moving faster. Okay, and so what I want to show you here, this is a pretty cool here's this word that we were talking about yesterday, derivation, right? So I'm going to show you where the equation comes from, okay? And then that's kind of cool to see it all come out like that, okay? So we know we're working with work, okay? So work is the sum of the forces in the along the path of the displacement multiplied by the displacement, okay? And so when I write down the sum of the forces, you guys should be thinking, oh, the sum of the forces from Newton's second law is ma. Okay, and so why can't I take that and put it in here, right? So you're gonna say, okay, well let's do that. So work is gonna still be equal to mass times acceleration multiplied by the displacement. And I'll label it specifically delta D for displacement. Okay. Now, I'm like, oh, okay. So it's kind of cool. We're seeing some like mixture of kinematics and into this work energy theorem. But could there be another way that I write that there, this delta D? Does anybody have any ideas? Could there be another way that we could write the displacement? What if I jumped over to my kinematics and I wrote something like this? V2 squared is equal to V1 squared plus 2a delta D. Okay. Well, you could write something in terms of delta D, but I think we could probably also write something in terms of the acceleration. What if I solve for the acceleration over here? What do you think is going to happen? Well, let's find out. So if I find out what A is, then I can plug it into where A is. So let's do that. So I'm just going to isolate for A. Okay, so I'll have A equals, so V2 squared minus V1 squared. That's going to be equal to 2a delta D. And then if I'm interested in getting the A by itself, I can divide both sides by 2 delta D, divide by 2 delta D. And what do you get? Well, the delta D's cancel and the 2's cancel, and A will be equal to B2 squared minus B1 squared divided by 2 delta D. Any issues with that? Anybody not like what they see on the screen? Trying to draw a box around it. Not going so well. Okay. So now that I've isolated for what A is, why can't I replace it over here? Well, let's do that. Work is going to be equal to the mass times A. Well, A we're going to say is B2 squared minus B1 squared over 2 delta D times delta D. Wow, when you're multiplying fractions, this is like over 1. What happens to the D's? Well, they cancel because they're in opposites, numerator and denominator. Well, what are you left with? The work is mass times V2 squared minus V1 squared over 2. Now, I know this we're going to just keep going with this, okay? And we're going to actually produce something. But let's pretend here for a second that you were to distribute the mass in, right? Or another way to think about it is you could remove the 2 from inside that bracket, right? You just pull it out because the whole thing's this is all multiplied by over 1, right? So I can take this 2 and move it outside of the bracket. Okay, and maybe it is best if we were to multiply the m in the first place, but we can now take this and multiply it into both terms, and we're going to see something interesting happen, right? We're going to see mv2 squared over 2 minus mv1 squared over 2, right? That's equal to the total work. That's the work energy theorem. And what it states is the change in kinetic energy is the work. Okay, so I'm just going to draw a box around this. Right? And what is this? Well, it turns out that kinetic energy is equal to, like the kinetic energy of an object we discussed up here, it was the mass and its velocity, like in combination. Well, kinetic energy is 1/2 mv squared. That's how you would v squared. That's how you would figure out an object's kinetic energy, how much energy it has. It's moving, right? So what this is saying down here is you have EK1, so the kinetic energy initially, and EK2. It's EK1 and EK2 because we're looking at the initial and final velocities, right? And we're subtracting them. Well, we know anytime I go like for instance, displacement, d2 minus d1, that was equal to delta d. So what is this equal to? Well, this is work total is equal to the change in kinetic energy. Does anybody have any problems with all that? It's a lot, and I'm never going to ask you to duplicate that, right? But it's interesting to see where that comes from. Okay, because we can actually use these two, right? Okay, so let's go down. So it is important to note that a change in the object's kinetic energy equals the work done. That's what this equation is telling us, okay? By the net force, which is the vector sum of all the forces, right? F net force, vector sum, right? So that's the sum of the forces is equal to MA. That's how we started this entire argument. Okay,
So let's just look at an example. Well, one more thing. So if the work is positive, then the object's EK increases, and if the work is negative, then the object's kinetic energy decreases. Okay, and that kind of gets to this morning, whether or not the total work is acting in the positive or negative direction relative to the displacement. Okay, so if the work's negative, is going to be working against the object, right? And so the kinetic energy or its velocity is going to decrease, right? And vice versa for when it's acting with it, it's going to increase. Okay, so let's just take a look at example 1 here. We've only got 2 examples after, well, 3 examples. Not too long. Okay, we won't be too long. So example 1, a fire truck of mass, here's the mass, is traveling at some initial speed, right? And has this amount of energy, or sorry, not amount of energy, it has that much work done to it, okay? Which causes the speed to become this, okay? We want to determine what the initial speed of the fire truck was given this amount of work was done to the fire truck. And you'll notice that it's negative, right? So we must know that if work is negative, the object's EK is going to decrease. So we better expect that the initial velocity would be higher than this number, right? Because if this is what it is, V final, V2, then VI must, or V1 must be bigger than V2. Is everybody okay with that? No arguments? Okay, so what I like to do is I just write down the stuff again. Like usual, I just write down the information that I know. Okay, I know WT is equal to, the total work done is going to be this negative 2.9 times 10 to the 6 joules. Okay, I also know the mass. Mass is 1.6 times 10 to the 4 kilograms. And I know V2, the final velocity, is 11 meters per second. That's what it became, implying that it was the final velocity. Okay, we want to find what V1 is equal to. And we know, just from our own, like, checking, like if we're checking our final answer, we know that the V1 value should be bigger than the V2 if negative work was done, because EK decreases in that scenario. Okay, so let's write out our work energy theorem, right? We know that the total work done is the change in kinetic energy. That turns into this, mv2 squared over 2 minus mv1 squared over 2. That's what this says. This is the change in kinetic energy. I thought I saw a comment come through. Sorry. Okay. So let's write that out. There's your list of knowns and unknowns, right? I'll get rid of this because we need the space. Okay. So WT will denote that work total, right, is equal to 1/2 mv2 squared minus 1/2 mv1 squared. Okay, this is the change. This is delta E. Okay, the change in kinetic energy, final minus initial, right? 2 minus 1. Okay, and now we're just going to throw the stuff that we know in. Well, actually, one thing, I want to push you guys towards doing these questions. This is a good example of if you were to plug in, just think, if you were to write this out, if I was sub 1.6 times 10 to the 4, V2 squared, like, just think 11 squared, like I'd have to plug in all these numbers over and over and over again. Well, look, I also see the mass here, right? So now I'm going to have to come over here, and this is going to be a real pain to have to type into your calculator. I mean, you can do it, and like it's just going to take you longer, right? But the thing is, maybe instead of typing a 4, you accidentally hit a 3 or something, and your answer's wrong now, right? So what I'm going to push you towards, as good practice, right, as you guys get more and more experienced in physics, is work with these things algebraically, right? So here's your expression. We want to identify the thing that we're looking for. I want to find the initial velocity.
well, why don't we just like apply some algebra skills that we have from our math courses and just get V1 by itself before I plug in all these numbers, right? So if you know that you want to find V1, then isolate for it algebraically. How do I do that? Well, let's just start. It looks like in both of these terms, I have a 1/2, right? So 1/2 m. So why don't I take that out? And what's left after I do that? We'll get V2 squared minus V1 squared. Now, let's move this stuff to the other side. Well, this is like m divided by 2, same thing, right? It's the same thing as 1/2 m. So if I'm dividing by 2 on the right side, then I can multiply both sides by 2, and I get 2wt, right? But then I could also divide by m, and that's going to be equal to v2 squared minus v1 squared. Have I lost anybody yet? Are we okay? Okay. I understand that for seeing physics for the first time for some of you, like plugging in numbers is comfortable, but it causes rounding error as you guys go through, right? But it also is gonna you're opening yourself up to typing a number wrong, especially when you're dealing with these big numbers like this, right? And so I want to eliminate that. How do you go from 1/2 m to 2? So Jagger, these two things are the same thing. So if I wrote something like this, Jagger, this is, let me write it cleaner, 1/2 m. M you could say is over 1. Okay, and how do we multiply fractions? Well, to multiply fractions, we multiply top times top and bottom times bottom. So you'd get 1 times m, well that's m, and 2 times 1 is going to be 2. So these two things are equal. They're just different versions of one another. Is that okay, Jagger? Maybe I'll go back one line here just to get. I take things for granted sometimes, but I also know that at one point in time that would have also set my brain on fire. Okay, so this is what happens after you moved the 2 over, right? Because the 2 would have canceled with the 2. Now you're at this stage. So let's move the m over now. Well, let's divide both sides by m. Well, now the m's cancel, right? And here's where we're at. We're at 2wt over m is equal to v2 squared minus v1 squared. What am I after? v1. All right, well, let's I don't know. We could take this. We could add a v1 squared to both sides, right? Which gets the v1 squared to the other side, or the v1. It's almost isolated. But then we could take this one and we could go minus 2wt over m from both sides as well. Okay, all I'm doing is 0 pairs. I'm just moving things from one side of the equation to the other. So if you guys don't like 0 pairs, all I did was take the, that was a faster way. I took the v1, I moved it to the other side, and when I do that, it has to change signs. And then I did that here as well. Has to change signs. Okay? And your final, here's what's going to happen now. You're going to have, if I swing this up here, I'm going to have v1 squared is equal to v2 squared minus 2 work total divided by the mass. And how do I get v1 by itself? Square root both sides. Now, although that looks a lot scarier, that honestly is a lot better than sitting there and typing in all these numbers. I can tell you that much. Okay? Algebra is scary sometimes, but really, algebra is just, it's working with letters instead of the numbers, right? The thing is like every line that you do a calculation,
chances are you might round. You might round like a 0.5 up or 0.6 up, right? Every line that you do a multiplication or a division, you're going to round, 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 round. By the time you get to this answer, you're going to have what we call rounding error, right? Whereas this way, I'm going to get an expression. I have an expression, right? V1 is equal to the square root of V2 squared minus 2 work total divided by the mass. So now you can plug in your numbers and round once. That's more accurate than round, 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 all the way through the question. All right? So just plug in your numbers. You know V2. V2 is 11 squared, or 11, but then you're going to square it. Then you got to subtract 2 times the total work, which was negative 2.9 times 10 to the 6, and divide that by the mass, which was 1.6 times 10 to the 4. Square root all that. What's V1 equal to? You guys can type that. It's a calculator exercise now, right? You type that in the calculator, you should get a V1 of 22 meters per second. Anybody freaking out? Okay, you see do lots of tutoring too, right? And you see kids like just want to type it in the calculator, but it's so easy. And the other thing is, for me marking your tests, if you guys make a I didn't type in a number correct, I can't find that. Your answer's wrong. You know how hard it is for me to go through your answer and to find out that you guys typed in a number wrong? That's really hard, right? Whereas if you solve it algebraically, let's say you ended up with a plus sign in here instead, I can find that error very easily, right? Oh, half a mark. There we go. Move on, right? It's also, if I can do it, you guys can do it, right? Because as you guys get a little bit more experienced in physics, you're going to learn that sometimes, let's say this answer didn't come out to be what we expected it to be. It came out to be less than 11 meters per second. Well, that wouldn't make sense. So then you guys would be like, oh, what's wrong? So I got to go find out why it's wrong. Well, can you imagine trying to find where you typed a number wrong in a test? Right? That's eating up valuable time, especially when you get to university and they tell you to put your pencil down and that's it. Right? You don't have extra time. That's it. Right? So wasting time trying to find where you've typed a number in incorrectly, you want to avoid that. That's what the algebra does. It'd be easy for you to find a sign error in algebra. Okay, but as soon as you start blending the numbers together because you've multiplied them, good luck. It's doable, but it's going to take you more time, right? These are the reasonings for me pushing towards algebra. Okay, I didn't really learn that till I was still on first year of university. It was rough for me, right? Because I was always typing things into the calculator, running out of time and things like that, right? Okay. Let's go through the next question. Okay. So here it is. A 27-gram arrow is shot horizontally, okay? The bowstring exerts an average force of 95 newtons on the arrow over a distance of 31 centimeters. Determine, using the work energy theorem, the maximum speed reached by the arrow as it leaves the bow. Okay, so let's again. Every time I have it doesn't matter. Math, physics question, it doesn't matter. I write down and extract what is given to me in the question and what it is that I'm looking for. That helps me immensely, right? Maybe it doesn't help you. I don't know. I'm just trying to give you. I've been through the struggle of this, right? Even to this day, I struggle with questions that I can't figure out. But no matter what, the questions at least get easier from the standpoint of knowing what you have and what it is you're looking for, right? Whether or not you can go from there is a different question. But at least having a starting point is better than just scrambling and reading the question 10 times and not look at. Anyway, write down what you know, what you don't know, right? Keeping in mind, sometimes you got to look what the normal units are that we work with, right? We don't work with centimeters. And we don't work with grams. What do we work with? We work with kilograms and meters. So those are going to have to be converted. Okay. So a 27 gram arrow, well, 27 grams is 0.027 kilograms. Right? You guys should know that 31 centimeters would be 0.31 meters. Okay. So let's go. Let's M equals 0.027 kg. We know the distance or displacement that the force is acting on is 0.31 meters, right? And we know the force is equal to 95 newtons. What is it we're looking for? Well, we're looking for the maximum speed, which is going to occur as soon as the arrow leaves the bow, so we could call that V2. We're looking for V2. And we know when we pull the bow back, it starts at an initial velocity of 0, right? You're going to hold it there for a sec, it's going to start at 0, and then you're going to let it go. So we also know that V1 equals 0. Okay, does anybody have any problems with what's going on? Okay, let's write out. We're going to use the work energy theorem, right? So let's write that out. WT is equal to, you could say just a change in kinetic energy, so we can write 1/2 mv2 squared minus 1/2 mv1 squared, right? Each of these, remember, being kinetic energy. We'll call this final EK, and this is the initial EK. Okay, so it looks like, oh, I know the mass. I'll just highlight things I know. I know the mass. I know, so that's that and that. I know V1 is 0. Well, that simplifies our life a little bit. And I know that's it. Okay, the thing I don't know necessarily right now is what this is. Okay, I need this in order to solve for V2. That's what I'm looking for, right? Well, we have a way to find out what the total work was. We said the total work done was the force times the displacement that something happened, right? And so we know the total work here, because there's only one force acting on it in the x direction, it's the bow. We know it's equal to force times the displacement, okay, or distance that the force was applied on. So force is going to be equal to the 95 newtons multiplied by, how long was it applying that 95 newtons? 0.31 meters. What's the total work done on this arrow? The number should be 29.45 joules. Okay, now we can use this number. Right? I can use this number over here. We can go, right? And it's up to you guys if you want me to solve this out. I don't know, algebraically or not. You know V1 is 0, so this whole term is going to disappear. Okay, so we know there's not much really to do. You're going to say WT is equal to 1/2 mv2 squared. Now we can just isolate for V2. Right? So 2 WT Did I lose anybody? Are we okay? All I did was, here's my starting point. What do I want to solve for the context of this question? I want to find what V2 is. So what did I do? I just applied my grade 9 and 10 math skills to arrive here. Right? I just did my algebra. And I got an expression for what V2 is equal to. Right? Now you can plug in all the numbers that you know. Well, now you know WT, right? That's that number. You know the mass. There it is right there. That's it. Right? So V2 is equal to the square root of 2 times 29.45 divided by 0.027. Right? And you should see that V2, or the speed of the arrow when it leaves the bow, should be 46.7. I think I keep calling it the bow. The speed of the arrow when it leaves the bow. Anybody have any problems, questions, comments, concerns? Got one more to do, and then you guys are free to go for the weekend. Okay, this is just this work from this morning, and with a little introduction of what kinetic energy is. And remember, kinetic energy is you can use kinetic energy to figure out, I don't know, what the mass of an object is, if you're given how fast it's moving, or here's the mass of the object, figure out how fast it's moving, if it tells you how much energy it has. Okay. Just watching the chat, see if anybody has any questions. Remember, you guys can send me private messages on Teams too if you guys have a question. I'll get those too. Okay. Let's do the last one. Okay. So a 61 kilogram skier coasting down a hill that is an angle of 23 degrees with the horizontal experiences a force of friction of 72 newtons. The skier's speed is 3.5 meters per second near the top of the slope. Determine the speed of the skier after the skier has traveled 62 meters downhill. Okay. And then determine the skier's kinetic energy after they've traveled the 62 meters. Okay, so that's part B. So let's start with part A, obviously. Okay, let's draw our free body diagram. Maybe we even start with that before anything. So free body diagrams too, they are also like, they're a way of writing all the stuff that you know down as well, right? And maybe I'll draw the slope this way because this is where our experience is. I'll draw it to the right. Doesn't matter, but okay. And our slope is at 23 degrees. And here's our skier up here at the top. What are the forces acting on the skier? Well, we got force of gravity. We're going to have the normal force as per usual, perpendicular to the surface. And backwards, if I get that draw, we're going to have the force of friction pointing backwards because it's opposing the object's motion, right, down the hill. And then we can break that force of gravity up into the components as per usual, right? We're going to have a y component that's equal and opposite to the normal force, which will take a value of mg cos theta. And then we're going to have an x piece that's pointing down the incline or the hill. That takes a value of mg sine theta. And it's sine again, remember, because it's opposite of the angle at the top. Okay, does anybody have any objections so far? Or are we okay? Okay, so we learned that the total work on a system is when we sum up the forces. And remember, the forces we care about are the ones acting in the same direction as the motion or the displacement, right? So down the hill, Remember, with inclines, we kind of set up our coordinate system to be positive down the hill, positive up, negative, and negative. Okay. So when I look at this, the motion or displacement is going in the positive direction. Okay. And the main driving force for that motion is this mg sine theta, right? It's pointing down the incline. And I also have the force of friction pointing backwards in the x direction, right? I don't care. We learned this morning about the normal force and this mg cos theta. They're perpendicular to the direction of motion. So the cosine of the angle would be either 90 or 270, both of which would create a 0 for that force term, that they're not doing anything for the work, right? And so when I look at the sum of the forces, the work total has to be equal to the sum of the forces multiplied by the distance or displacement that those forces are being applied on, right? And so we're going to look at what the forces are that are acting in this direction of motion, d, right? And so we're going to see, okay, well, I have a positive mg sine theta. And what else do I have? Well, the force of friction that's acting negative, right? And that's going to be multiplied against the length of the hill, right? 62 meters. Anybody have any objections? That's the algebraic. That's what the algebraic expression is for the total amount of work. Okay, it's at this point we can plug in all the information we need, or that we have, I suppose. Not what we need. Okay, so this is almost like part A. This is part A, not almost. It is part A. Okay, what are we after? We're after the skier's speed at the bottom of the downhill, or after 62 meters anyway, right? So we need V2. And it also told us, V2 is what we're after. V1 told us that it was 3.5 meters per second. Okay, so when I go to write out the work energy theorem, again, WT is equal to the change in kinetic energy, right? And so we're going to see 1/2 mv2 squared minus 1/2 mv1 squared. But again, the problem is, much like the last question, I don't know what the total work done on this system is. That's what I'm using this for. Okay, because I know everything in here. I know the distance that the forces are acting on. I know the force of friction, and I know m and g. And I know the angle of the incline. So you can use all of this to find out what WT is. You can take WT after and plug it in here. All right, so let's just, for simplicity's sake with this question, let's just find what WT is using the stuff that we have in the question. So the mass, 61, multiplied against 9.8 sine theta. We're going to subtract off the force of friction that told us, force of friction kinetic, 72 newtons, minus 72. And all of this is going to be multiplied by the distance of 62 meters. Okay, and when you type that all into your calculator, you should also replace the theta value to be 23. Okay, when you type this into the calculator, you're going to see you get a total work for the system of 161.6 joules. That's the total amount of work being done on the system, on the skier. It came out positive, right? So you better expect that if the work that's done is positive, you better expect that the velocity increases by the time they get to the bottom of the hill. And that seems to have been, that's intuitive, right? But this is the physics behind why. Okay. If the force of friction came out to be more than this mg sine theta term, then the skier would be slowing down, right? I'd see this value come out to be negative, and so then the forces acting on this object are causing it to slow down, and the work is negative, right? And then I would expect my answer to be less than the initial velocity that it started with at the top, right? Maybe you have like you didn't wax your skis or something, right? And you were moving slower than you would have if you increased the friction somehow, right? Okay, so now we know WT, right? Let's just solve this one with numerics. Like we'll just plug in the numbers. Okay, so we know 161.6 is WT. Okay, we know the mass, right? Like I would just get in the habit of like I'd factor out the 1/2 just to be like I just don't want to type as much, right, into my calculator. Okay, and then I can multiply both sides by 2. So I'd get 2 times 161.6 divided by m. Whatever m is, doesn't matter. Right? And I'm after what V2 is, so I'm going to move the V1 over. So I get 2 times 161.6 divided by the mass plus V1 squared has to equal V2 squared. And we know that if I square something, I got to square root both sides, right? And so V2 is going to be equal to all of that. All right. And when you guys do the actual math, I'll plug in all the numbers so that we all know we're on the same page. Did I forget to multiply by 62? Did I, Jagger? I don't know. Possible, I suppose. Maybe I did. Is my work supposed to be bigger than that? It's possible. That's a good point, Jagger. I don't know. I'll type it in. Yeah, Jagger, I forgot to multiply. Sorry. Does this look better, Jagger? Sorry. Thank you. Is that better, Jagger? Is that what you got? Okay, good. Okay. Well, you know what, guys? Here, let's just do this. I'll continue to emphasize the importance of algebra, and now we're at the stage, just plug in your numbers. Okay, so we're going to have 2 times 10,018 divided by 65, I believe, 61, plus 3.5 squared is equal to V2. That's all has to be square rooted. So now I actually have to do this, Jagger, because I had the wrong answer before. Okay, so we got to do 2 times 10,018, right? Divided by 61. This guy should see 328. You guys tell me if I get anything wrong here. Okay, you jump in. Plus okay, that's part A. That's the answer for part A. All right. Part B is really short. Okay, does everybody agree with that one now? Thanks, Jagger. Okay, part B. That's the velocity that the skier has after they have traveled 62 meters. Okay? Now, we want to determine what the kinetic energy is. So we can say, okay, well, I know, and it's basically going to be EK final, right? Well, we know what kinetic energy is. I told you a couple times today. We wanted to find what the kinetic energy of an object was. We take 1/2 multiplied by its mass multiplied by its velocity. So I'd get 1/2 of the mass, 61, times 18.5 squared. What do we get? I don't know. Let's find out. 0.5 times 61 times 18.5 squared. The skier's kinetic energy, the number's too big to fit there, I think. Maybe not. 10,438.6 joules. It's a lot of energy. Right? Where does that come from? It talks about like how do you increase an object's energy? Well, you can make it more massive, right? Or you can keep the mass the same and increase its velocity. Both of which will create higher amounts of kinetic energy. Okay? Increase mass, increase kinetic energy. Call that proportional, right? Increase the velocity. Actually, the velocity increases it twice, by a squared amount, right? Because the velocity is squared. So it's not directly proportional, but you increase it, it increases. Okay? Does anybody have any questions?